math is good. Do our role-playing game. It's like an RPG. Oh my gosh, let's see. So is there anything, yeah, maybe something you have for me? I see like Camila's got something out. Can I grab those, please? Thank you. I know I got yours already. Thank you. Did I get it already from you in real? Or in Calc 3? Yeah, okay, cool. I think I got yours too already, didn't I? Okay, great. Thank you. All right, let me grab my notes. I know we're going to talk more about series today. There's like some little tiny details I want to talk about. I don't want to miss them. Alrighty. Okay, so yeah. Gosh, did I start that, Liv? Can you see if that's even recording? Yeah. Okay, cool. Thanks. Last time we started talking about, ooh, purple, I like that. That already made the day better. Infinite series. And we talked about what are the two kinds of series we know and totally understand. Geometric and p-series, right? So we have that toolkit of the geometric, and those are ones that look like this. And I'm not going to put indices here. We can always assume there's an infinity on top. It doesn't really matter where it starts. But it's something you want to keep in mind, especially if you're trying to find the sum. And so we have geometric, and then we have p-series. Oh, when does this converge? What's the condition on that? Beautiful. Magnitude of r is less than 1. And then we got p-series, spelled pretty poorly. And that looks like this. And this honestly could start anywhere as well, and it's going to run to infinity. When does this converge?
When p is greater than 1.
Thank you. Yes, ma'am. P is greater than 1. So convergence. These are just facts to have ready. There's some other types that we'll probably get to, but these are our main kind that we can really fully understand. And we will use them over and over again as comparisons. So in infinite series, I didn't really get into the generic part of this last time. I'm going to actually start this guy at 0 here to infinity just to write it out. So this is the sum of a bunch of real numbers. And I want you to maybe think back on how we got to understanding this. And remember, if r was less than 1, we came up with this formula that it converged to that if r was less than 1 in magnitude. And we got there by looking at finite sums. So the way to understand these, so the way to understand a series is by turning it into sequences. So we spent like a month or more talking about sequences, lists of numbers, and when they converge. And the way to understand series is via sequences, and it's very particular sequences of what are called partial sums. So what do I mean by that? So the first partial sum, let's start this at 1, just so this, let's start that guy at 1, just, it'll make this notation better. The first partial sum, s sub 1, is just the first term in the series. So there's not much of a sum yet. The second partial sum is the sum of the first 2 elements of the series. And so what we're going to do is grab these finite bites of the series, moving further and further out. S sub 3 is the sum of the first 3. And then S sub n, we can write this out, is equal to a sub 1 plus a sub 2. It's the sum of the first n terms. So by looking, we turn this thing that's this infinite list of numbers into a sequence of numbers. And what we say then is the series converges if and only if the sequence of partial sums converge. I'm halfway between too cold and too hot. I don't know. I'm just gonna leave this little shirt on here a little bit longer. And more particularly, if the sequence of partial sums converges to some number L, we write that the series is equal to L. That's what we mean when we say it equals some number. So let's take a look at some series and thinking of it in this way. We thought about it a slightly different way last time. Let's do that guy, classic kind of terrible series. But let's look at the partial sums and see that this doesn't converge in a different way than we did last time. I think last time we saw that this didn't converge because the terms weren't dying out. But we can look at that from this perspective here. So S1 is just the first term. It's just 1. S2 is the sum of the first two terms. It's 0. What's S3? One. I'm going to add a 1 to it. Right, this guy here, maybe it helps to write it out. This is -1 to the 0, -1 to the first, -1 squared, -1 cubed. So this sum would look like this if I wrote it out. So S3 is the sum of these first three things, and that's just 1. And we can kind of get this perspective then that the even sums and the odd sums are going to be 0 and 1 respectively. You either just canceled the 1 out or you just added the 1 back in. So let me ask you a few questions here. So with this sequence of partial sums, S sub n for this guy, what is the lim sup of S sub n and what is the lim inf of S sub n? Sequence looks like that. Liv, what do you think the lim sup is?
1.
It's 1, yeah, absolutely. And then what's the lim inf? 0. So we've got these subsequences. I've got this subsequence in here of things that are constantly 1 and the subsequence that's constantly 0. This guy heads to the lim sup, this guy heads to the lim inf. And we had a result that lim of some x sub n exists if and only if the lim sup equals, I'm just trying to review some stuff too, the lim sup equals the lim inf of x sub n. So here we can see this sequence does not converge. So the series does not add up to anything. So sequence, so S sub n does not converge. So the series does not converge. This is great. Already feeling better. Just got to start doing some math. Start LARPing some math. So now let's get a couple results out here. Because now that we understand this, now it's starting to get hot. There we go. Now I'm getting warm. World's gonna be okay, finally. It's 15, it took me, 10 minutes to get the world's gonna be okay now. It's gonna be all right, guys. In 4 years. Hopefully. All right. So we've got a couple key results that we need to do the things we want to do, because our goal is to take, let me show you where we're going to head today. I want to take a series that looks like this. Let me get out some of my weird ones here. So our goal is to be able to determine if an arbitrary series converges. And so here's kind of a cool one. I've never actually even seen this one before. I saw it in our book as a problem, and it's kind of cool. So, e.g., does this series converge? So some, probably we can start at 0. I don't think it matters here. 2 over -1 to the n minus 3 to the nth power. That's pretty wild looking. First thing you should do when you see something nasty like this is figure out what it is, right? So let's just take a minute. What does this series look like? Go for it. Take a minute. Start with n equals 0. I think that's right. Let me know. Is that yeah? Okay, cool. It's pretty weird. Once you get what's going on, you can kind of extrapolate, I think, to that. We could actually answer this question right now, if that converges or not. We don't need, I wanted to use this as a fancy test example, and we still will come back to it. But what do you think? Does this series converge? Why do you say that, Christian? I agree.
Because the limb soup would stay at 1, and I think the limb inf would be 0, because like the fractions are getting smaller as you keep going.
Cool. So I like the way you're thinking of you're taking. So this was the limb soup of the partial sums. But no, it's okay. But you're thinking absolutely the right way.
I guess like more so like as with the entries in like this series, like you kind of stay at 1 versus like the bottom side. Is
Yeah.
approaching
Yeah.
0.
So there's always going to be these. Every other term is 1. And remember, we had that result. What does the nth term test say? Or the divergence test? What does that say? Yep. If the a sub n's do not converge to 0, if the terms don't die out, then the series diverges. So we can immediately, so you're right, Christian, it does diverge. The reasoning, we had to tweak a little bit, but yeah, you saw what was going on here. So this series diverges. Because in fact, and here we could say that the limb soup of the a sub n's, the terms, is 1, and the limb inf, and notice here I'm not saying partial sum, I'm just saying the terms of the series, and the limb inf of the terms. I think you're right, Christian, it looks like they're shrinking to 0. Yeah, I think 0 is the right answer there. Those tiny little, because these guys are just definitely shrinking to 0 from the negative side, so yeah. Cool, so we know that diverges, but what if I gave you one that's a little bit not as clear? For example, what about this series? This guy. Let's just take a look at it for a minute. Does the divergence test apply here? So take a minute and be careful with your answer. So I'm asking, what is this limit as n goes to infinity? You know, one of the things that I was kind of like bummed about this morning is Dr. Gray's leaving. Like he's going to France to do research for the next year, but he's like, I'm getting an extended visa. He said for 3.5 years for some reason, and I just, honest God, I hope he comes back. I feel like it'd be a huge loss to lose Dr. Gray. Cormac, did you take that limit? You kind of look like a man who took a limit just moments ago.
I think that it does converge because I said that the limit goes to 0.
Ah, okay, cool. And I like that you said that. So you're saying that since the limit went to 0, the series converges?
Yes.
that what this?
That's
That's not exactly what this says, is it? And let's actually think about that. I'm glad you brought it up. So these do go to 0. You're absolutely right. This limit does go to 0. You can think the top is just not blowing up as fast as the bottom. But that doesn't mean convergence. So this does not imply convergence. And I want to just give you an example right here. Think about this series, 1 over n to the 1/2. That's a p series. P equals 1/2, so it diverges. But the terms definitely shrink to 0. They just don't shrink fast enough. They don't die out fast enough for that to happen. So cool, thank you. I owe you $5 or something for helping us remember to talk about that point, because it really is important. And it's a super common logical mistake. Okay, so what kind of series does this look like? What was that? I heard it. So it kind of looks like a P series, right? Because and we're thinking, oh gosh, it kind of looks like there's like this base that's moving. There's fixed exponents. It doesn't look like a geometric series because there's no moving exponent. So it feels like a P series, but how do we move from feels like a P series to knowing if it converges or not? And that's what we're going to talk about now. How do I link any arbitrary series like this to another series that I understand? So that's what we're about to do. We're going to talk about some tests for taking an arbitrary series and comparing it to our toolkit of series that we understand and making some conclusions. That's the plan. So, towards that plan, what's our first test here? Oh yeah, this is, actually I kind of want to make just a side point that'll help with all of this. Just one last perspective on series tails. Because the tails this is where convergence or divergence happens. It's all about what happens at infinity. It's never about the first 1,000 billion terms. It's always about the limit at infinity. So tails of a series determine convergence. You cannot screw up a series in the first billion terms. It's only with infinity that things can go bad. So first off, we know this. We know that if this series converges, that happens if and only if the sequence of partial sums converges. So this S sub n, let me just refresh your memory about what that means. Where S sub n is the first n terms, so it's the nth partial sum. So this converges if and only if this converges. That's literally the definition of that thing on top converging. This is a sequence of numbers. So it converges if and only if that sequence of numbers is Cauchy. Now we're making a big leap. Remember that every Cauchy sequence converges, and every convergent sequence is Cauchy in the real numbers. So let's think about what does it mean for this sequence of partial sums to be Cauchy. So, i.e., for all epsilon greater than 0, there exists some place down the line, n, so that if, I'm going to write this a little bit differently, m minus 1 and n are bigger than capital N. This could just be m. It's gonna make things prettier if we write m minus 1 here, and you'll see in just a minute. So that if m minus 1 and n are bigger than that cutoff, normally we would just have that, just that m. But subtract it off. So just make a little note here, minus 1 for notational prettiness. And we're also going to assume here that n is bigger. Also, let's assume that the n is bigger than the m minus 1. One of these two has to be bigger. Let's just assume it's like that. It'll make what I'm about to write a little bit better. So to say this is Cauchy means you give me an epsilon, I can find a spot down the line where we have S sub n minus S sub m is less than epsilon. That those two terms are getting arbitrarily close together, no matter how far apart those two terms are. Is this ringing bells? Is this feeling Cauchy-esque? Yeah? Okay, cool. So let's write out what that means, i.e., these are partial sums. So this is a1 plus a2 plus, oh, sorry, this should be m minus 1 here, sorry. Yep, m minus 1, because that was what I pulled there. Plus a sub 3 plus blah, 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 plus, now, in here somewhere is a sub m, and then I keep going and I get to a sub n, because remember n is bigger than m here. So somewhere in there, and put it in there because it'll help your notes if you look back at them. So this is s sub n right here, and I'm going to subtract off s sub m. So that's a1 plus a2 plus blah, 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 plus a sub, and actually sub m minus 1. This is s sub m minus 1 right here, and that's less than epsilon. I heard it's pretty easy to live in France. Just need to have some kind of basic income that's like French minimum wage. You can go there forever. I've known a few okay French people. Maybe one that wasn't that great. You know, people are of varying qualities everywhere. So, i.e., what is that left thing, what is this simplified to? What is that subtraction simplified to? Yeah, exactly. Because this piece here right in front of this, and I probably would have helped if we put, there's a sub m minus 1 right there. And we're literally subtracting off this whole chunk. So what this means is i.e. a sub m plus a sub m plus 1 plus blah, 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 all the way up to a sub n. Now you can see why we picked m minus 1 over there. Just so this looked pretty. We had to pay the pretty price somewhere. And it's nicer to have it at the end. It's less than epsilon. So let's summarize really quick what just happened. Summary. The series converges if and only if, for all epsilon greater than 0, there exists some place where if I pick some m and n bigger, now I'm just going to go back to m and n, bigger than n, we have the tail between these two indices is arbitrarily small. So let's write this out, put this here. let's talk about it. This essentially means the tail is dying out. You tell me how small you want the tail to be, and I can find a spot where no matter what chunk of the tail I pick past that point, it achieves that smallness of magnitude. So the kind of loosely, ooh boy, oh yeah, that's a good pen. Loosely, the tail of a convergent sequence must die out, i.e. head to zero. We kind of knew that, but this is a much more open interpretation that's actually going to help us prove a couple of things much more easily. Notice this is an if and only if. The nth term test is a special case of this. So just make a little note that that divergence test is a special case of this. Okay, let's prove some stuff now. Okay, so our first big test is the comparison test. And this is actually, sometimes this is called direct comparison, especially in Calc 2, direct comparison test. And let me get the statement up here. So we've got some series, a sub n, and the terms are non-negative. This a sub n is going to be our comparison series. This is going to come from our toolkit. So this will be something we understand. The understood reference series. And sometimes these are called positive term series as well. So this first result is if this series converges and I've got these other terms, b sub n, and their magnitude is bounded by the terms of that series for all n bigger than, how about we just say bigger than or equal to some capital N, because it really just has to happen at some point. It doesn't really matter. It could fail in the first 1,000 terms, but if eventually this is true, let's make a little note here, eventually true for all terms past some point. Much better to have these things in the general. Then this series converges. So this b sub n, this is probably the thing I was given and asked to determine if this converges or not. And so I find the appropriate series that I understand and hope that this condition is met here. So this test is used to show convergence. You can't really show divergence with this, but you can show convergence. But we can show divergence with the second half. 2. If the sum of a sub n is plus infinity, i.e. it diverges, since all the terms are non-negative, things aren't going to cancel. You're not going to get plus 1 minus 1, plus 1 minus 1, plus 1. Everything will either add up to a finite value, case 1, or they will add up to positive infinity in the divergent case. So if I know that that series diverges and the b sub n's are greater than each of the terms on this thing for all n greater than or equal to some cutoff again, then this series diverges. Let's actually put that to use and then talk about the proof. So let's go to this guy that I had up to begin, so example. What did I have there? Plus 2? 2, okay. So we were asked to think about this series, and we all agreed that feels like a P series. So, feels like a P series. Now we have to figure out what P series it feels most like. Any thoughts on that? Because I'll show you a couple ways to think about it, but what do you think a good, is this the P series we're thinking about? Think about when n is large. What is the effective term here? You got some, Cormac? Yeah.
I was gonna think just 1 over n.
Yeah, why do you think that?
I think it's really big. N over 3 will cancel out from n over 4.
Yeah, when n is big, so think about having 1,000 cubed over 1,000 to the 4th plus 2 doesn't matter much. And this is approximately 1,000 cubed over 1,000 to the 4th. And that's approximately 1 over 1,000. Well, that is exactly 1 over 1,000 right there. So it feels like, and if I compare the powers, there's a cube on top, a 4th on the bottom. So it feels like the harmonic series. So it feels like a P series. In particular, it feels like this series. The harmonic series. Does the harmonic series converge or diverge? What's that? Diverges, definitely. This is a P series, right? It's just a special P series with P equals 1. And P series only converge when that P there is bigger than 1. So this is actually the cutting off. This is the cutoff for convergent divergent P series. And so this diverges. So now I'm already thinking, okay, this thing diverges. Because I'm thinking it looks like something that I know diverges. So now I have to apply the test. So let's compare the terms of our series with the P series. And you can't just say it's like this. You need to be precise. We need to actually show some things here. So for us, the B sub n's are the things we're given. And the A sub n's are the terms of P series. Now what I need to have happen is what? Which of these two conditions over here am I hoping to get? Yeah, because I'm looking for this case right here, right? Here's what I want. I want this. Do I have that? at least the way things are written currently. Let's look at some ends, right? Let's just pick a couple here. It's actually, maybe if someone could give a calculator out, that would be pretty cool, or a phone, right? So let's do some ends. Let's do the B sub n, and then let's do the A sub n, just to get a feel. So let's do n is just 10. And so I've got 1,000 over 10,002 versus 1 over 10. Which of those numbers? Yeah, so we know what this one is, but what does this turn into? Is this bigger than that? So that's the question. You might be able to figure it out without a calculator. What do we get here? This is approximately, this is 0.1. What's this approximately?
0.09998.
And it's not bigger. So I can't, the way this is written, I cannot directly go to this, even though I know it's gotta be right. Because when this n is big, this thing is definitely like that. So it's the right comparison. So we need to do some work. We need some algebra. So let me show you a few tricks here. Notice that n cubed over n to the 4th plus 2 is bigger than or equal to, let's see, so we got bigger than, strictly bigger than, n cubed over n to the 4th plus 2n to the 4th. Why is that so? Why is that so?
Your denominator is growing faster.
Yeah, I made the denominator bigger, right? So as soon as n is bigger than 2, this actually, when you put this here, it's equal when n equals 1, but past that, I just made the bigger denominator. So that definitely has to be true. Now I got a little algebra here. This is, oh, good, nice. And now things cancel. So this is actually 1/3 1 over n. And so what I actually now have is that 1/3 of the harmonic series terms are bound underneath this thing, but I had to do that little bit of a tweak. So let's write this up on the right side here. I'm actually going to ask you to read that proof. If you would read through this section, that would be great. I think it'd be more fun today to just work on some applications of tests. So, since this series diverges, we know that 1/3 of it diverges. If this is infinity, 1/3 of infinity is still infinity. And since 1/3 times 1 over n is underneath the terms of our series, so watch how I'm writing this all out very carefully. Well, now it's careful. By the direct comparison test, our series diverges. By the DCT, our series also diverges. Okay. If I want to show convergence, I need to find something that bounds it above and keeps it from shooting up to infinity. we'll get to a few examples, but let's get another test up here first. And maybe a definition here, just really quick. Definition, a series, sum of A sub n, is absolutely convergent if I remove any possibility of subtraction and I just add the absolute values of the terms. If this series is convergent, yes, that's right, that is what I wanted to say. So let's do a quick example. So let's take a look here at the alternating harmonic series. This is the alternating harmonic series. Alternating always means there's a plus minus game going on. Is not absolutely convergent because its absolute version is the harmonic series. Is not absolutely convergent because its absolute version is 1 plus, just take out all the alternation, the harmonic series. Now I kind of feel like I want to show you one more proof that the harmonic series diverges, just because we understand the comparison test now, and this will be great. This is a cool way to see it. I think I showed you with the integral test last time, but this is a much more intuitive way. Recall that the harmonic series, I guess I really just want to make sure that this is something we know deeply in our hearts. Recall that the harmonic series is divergent. So here's a quick proof. Quick proof using the direct comparison test. This is cool. This is a fun little game. You're gonna love this, I think. I think you're gonna love this, because I kind of love it. So let's write out the harmonic series, but let's write it out in kind of its full glory up to the 1/8. And then let's do 1/9, and then blah, blah, blah. Go up to 1/16, and then 1/17 plus blah, 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 1/32. And then from there on out, I think we'll see it. So make sure to incorporate all those little deets that I have there. We're going to group some things together. So I'm going to put a little brace to group together the 1/3 and the 1/4, and the 1/5 through the 1/8, and the 1/9 through the 1/16, and the 1/17 through the 1/32. And kind of imagine this going, but you might not see exactly what the grouping rhythm is yet. So we're going to put that this is greater than here, and we're going to write some stuff underneath. So I'm just going to copy the 1 down, plus, I'm gonna copy the 1/2 down. Those are the same so far. But here, I'm going to bring down 1/4 plus 1/4, because a third is bigger than a fourth, right? A fourth is smaller. I just made the denominator on that guy smaller, so these two are the same. So these two, that is a greater than relationship right there. Does that make sense the way I'm writing this? Yeah. And so then these guys here are greater than, I'm going to replace each one of them with 1/8. And I'm grouping those together. Notice there are 4 of them. Notice there are 2 of these. And then we'll move out here, and we're going to replace, what do you think I'm replacing all of these with here? 1/16, that far end term. That's a power of 2 in the denominator. So then these guys are going to be greater than 1/16 plus 1/16 plus blah, 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 plus that final 1/16. And then out here, again, greater than, now I'm gonna do 1/32 on all these. So it's gonna be 1/32 plus 1/32 plus that final 1/32. And then you see the next one would be 64th. But now let's take a look. How many of these things are there? So first off, notice here that these add up to what? Just these 2. 1/2. There's 2 of them. What does this add up to? 4/8. 1/2. What does this add up to? How many of these are there? 8. There are 8, right? Because it goes 1, 2, 3. Yeah, there's 8 of them. so this adds up to 1/2 as well. And then this adds up to 1/2. And if we keep doing this grouping, what we see is that the harmonic series is greater than this series that looks like this. And that sure the hell piles up forever. Terms don't die out. There's no way that this doesn't just keep adding up to infinity. So that's a cool proof. I like that one. Very different mode of thinking. So this one actually turns out, and we'll see this probably next Monday, this does converge, in fact, the alternating harmonic. In fact, it actually converges to the natural log of 2. That you can prove this. Remember back in Calc 2 when you did series expansions? If you look at the series expansion of natural log of 1 plus x, if you look at the Taylor series of that, it basically, and then you let x equal 1 here, you get that series there. I don't think we're doing that, but that's how you could see it. And so that's this another cool fact to know. Hey, what was this one? Do you remember? What was that? That did converge because it's p series, p is greater than 2. What was that? Because I want you to leave here where you're always like, you can just pull these up and impress people. If nothing else, like this cool little fact, you're like, does it look like you're computing it? Just think about it for a minute and then say what? Then you say pi squared over 6. And everybody's impressed. That one's way hard to prove. All right, so one more test. And this one is a baddie. I mean a goodie, but it's a badass test. Probably one of these 2 tests are going to be the 2 you're going to want to use more often than not. So, the first test is the root test. You might have seen this in Calc 2. You probably didn't if you took Calc 2 with me. Probably didn't talk about this because we were probably desperately trying to just get through everything at the end. So, I've got a series sum of a sub n, and the a sub n's are not 0. None of them are 0 terms. This thing converges absolutely. Converges absolutely if the limb sup of, one last thing, define one thing up here. Define alpha equals the limb sup of the coefficients a sub n, their absolute value to the 1 over nth power. So here we're taking roots. That's why it's called the root test. This is actually just the limb sup of the nth root of the absolute value of the nth term. So the series converges absolutely if that limb sup is less than 1. It diverges if alpha is bigger than 1. And the test is inconclusive if alpha equals 1. And let's just get the other test up. So that is the root test. Let's get the ratio test up. And I think we're kind of at least done with tests for today. We're just gonna play some games. And I do have a homework assignment for you, which is a lot of series to look at and apply these things to. So the ratio test says we've got a series, a sub n. The a sub n's are not 0 again. Define, so it's a slightly different alpha, but it's a very similar idea. Alpha is equal to the limb sup of the ratio of subsequent terms, the absolute value of the ratio of subsequent terms, so the next term to the previous term. You're going to see, we actually have the exact same results here. So if alpha is less than 1, the series converges absolutely. If alpha is bigger than 1, I'm saying these in slightly different orders, the same thing. The series diverges. And again, we have inconclusive results if alpha equals 1. And we need to take some other methods up. So these inconclusive cases, these are like further analysis is required. All right, let's do some tests. How about this series here? Sum n equals 1 to infinity, n cubed over 4 to the n. Now I'm going to talk this through because it's kind of a mishmash of different fields, right? It's got like the geometric moving exponent, but it's also got this just base that's got a fixed exponent moving, so it feels somewhere between a p-series and a geometric series. So for this, we could try the root test, but that's going to feel a little painful. So let's just try it first. Let's try the root test because there's a moving exponent. Anytime you have a moving exponent, the root test is a good bet. So the root test says we're going to figure out what the limit superior is of, so a sub n here is this guy. Absolute value doesn't matter because everything's already positive. So I'm going to take the nth root of this. So now I've got to do some algebra. And we're going to, and this is certainly going to become, at least to me, I immediately see something that I don't like. The bottom's nice. What's the bottom simplify to? So we got this on top, we got this on the bottom. 4, just 4, right? The x, you multiply the exponent. So the bottom's just 4. Okay, awesome. But then on top I've got that. And I'm just curious if you know, like we can do this. What though is the limit as n goes to infinity of n to the 3 over n? Do you remember how to do that? Maybe we should talk about it so that we could do it, but we don't want to. Does anyone remember how to do that kind of limit? Because you've got a base going to infinity and you've got an exponent going to 0. And that could be lots of things. Do you remember the technique? No? So it goes like this. So we're going to call that L. I'm going to take the natural log of both sides. And I'm going to do a funky move where I pass the natural log inside the limit. I think it's good to see this because it's probably been a long time. What can I do with that exponent? Bring it out in front. That's why I took the logs. Now, at least now it's out of the exponent. So this is equal to lim as n goes to infinity, 3 over n, natural log of n. All right. And I'm going to write that as, I'm going to pull the 3 out in front, limit as n goes to infinity, natural log of n over n. How do I do that? What is that limit? Let me start clearing up the board over here. And whenever you have a ratio and you're doing a limit and the top's moving and the bottom's moving, first thing you should do is see where each piece is going to. Where is the top going? Infinity, because natural log of n as n goes to infinity is infinity. So this thing here is an infinity over an infinity form. How do you deal with infinity over infinity forms? L'Hopitalin. Exactly. So by L'Hopital's rule, this is the limit as n goes to infinity of, what's the derivative of natural log of n with respect to n? Wait, what?
Is it e to the n?
Yeah. I like that. It's 1 over n. Yeah. So d dx natural log of x. 1 over x. Yep. So this is 1 over n on top, and then what's the derivative of the bottom? With respect to n? Just 1. So what's that limit? 0. But that wasn't exactly the limit I wanted, right? That's actually the natural log of the limit. So, and we also had this 3 out in front here also, but it doesn't matter, it's 3 times 0, so it's just 0. So the natural log of our limit is 0. What is my limit? Yes, say it. That's right, it's 1. Yes, you're making the 1 mouth. Yeah, so L is 1. So that was this piece right here, right? This piece was going to 1. So the full ratio is 1/4. All that work was just for this top piece. That went to 1. So the final limit is 1/4. That is less than 1. So that's our alpha. It's less than 1. So this series converges absolutely, if we had to worry about that. Let's write it. Converges absolutely. And you want to say by what test? By the root test. Let's use the ratio test and see how that rolls a little differently. So, using the ratio test. We have alpha now is the lim sup of the ratio of leading of subsequent terms. And I like to rewrite this. So this is lim sup of the n plus first term times 1 over the reciprocal of the preceding term. Let's write up here what a sub n was. I'm going to pull out the arbitrary term. It looked like this. And then I'm going to write it in the way, the goofy square fill in the blank way that I do, but it's, you know, it honestly does a lot for your brain, especially when we're working with these indices. Could you take a minute on that? So here's a sub n. You need a sub n plus 1. That means you just got to replace that box with n plus 1 and get that. And then some things will cancel, some things won't. You might find this limit easier to take, because at least you don't need the logarithmic stuff. I got P. I'll be right back. Just flip that fraction, it makes life a lot easier. If you wrote this as a complex fraction with fraction over fraction, probably looks painful. Maybe feels painful. But notice we still get that 1/4 that comes out in front when these two things cancel. And then we're left with this limit. And what's that limit? Cecil, what do you think that limit is? Should we talk about it? Talk about it? Okay, all right, cool. So let's when n is super large, when n is 1,000, what is this ratio approximately? What's 1,001 cubed over 1,000 cubed? Kind of 1, a little more than 1. We could also write this out if you knew how to do the expansion of this. And there's some basic facts for limits you definitely want to have in mind. If you were to FOIL this out at the super FOIL that this requires, the binomial expansion, the first term, I hope that you see the first term would be n cubed. First off, I hope you don't think that the answer is this. That's only part of the answer. There's other shit that happens in there. But certainly the first thing is n cubed. And then it would be 3n squared plus 3n plus 1. Notice that last thing, your constant term would be 1 times 1 times 1. So that you'd have that. So we got that over n cubed. Now I could look at this as I have a ratio of polynomials. And I'm looking to take the limit as the variable goes to infinity. When they have the same degree, the limit is the ratio of the coefficients. When the bottom one is bigger degree than the top, the limit is 0. When the top's bigger degree than the bottom, it could be plus or minus infinity. Depends on the ratio of the signs. So this limit here is just going to be 1. But if you wanted to, you could even expand this out just to prove it. That's n cubed over n cubed plus 3n squared over n cubed plus 3 over n squared plus 1 over n cubed. It's easy to see all those guys go to 0, for sure. A bunch of different ways to look at it. So in the end, the limit is 1/4. That is less than 1. So this converges absolutely by the ratio test as well. So I've got some stuff I want you to work on over the weekend. Let's see if we can try to hand this in on Monday. Some series to analyze. There's no proofwriting here, but I mean these are you still give me an argument. Use some flow words, kind of like we've been doing here. Tell me what test you're using. Show me the test, please. But the series that I'd like you to look at, and I'll have your other ones back to you on Monday, for sure. Slightly bigger homework assignment, but yeah, there's not proofs. So 14.1, A, B, and F. 14.2, E and F. 14.3, B and E. 14.4, just A. 2 more, 15.1B and 15.4C. And some of these will be pretty easy. Always look for low-hanging fruit, right? If you think that the divergence test, if you can look at the sum, and you can see like oh, they're asking me to add that up. Those terms don't die out. That's super easy. I can immediately conclude divergence. So sometimes the divergence test gets you out of any work really quickly. Keep an eye out for that. All right, my friends. Sound good? Sound okay? All right. Thank you. Let's see how the